Well, good morning. My name is Andrew Penny, and I'm going to be talking about some of the recent improvements that we've made to the probabilistic storm surge model, or P-Surge. First of all, I'd like to thank my co-authors, Laura Alaka, Cody Fritz, Jamie Rome, and Arthur Taylor. So the operational storm surge model that we use for guidance at the National Hurricane Center is P-Surge. And P-Surge is an ensemble of slosh forecasts. Slosh stands for the sea, lake, and overland surge from hurricane model, and it's really a computationally efficient model. We can run thousands of simulations within the operational time window that we have, which is typically an hour. The P-Surge ensemble accounts for uncertainty, or attempts to account for uncertainty in the cross-track and along-track directions, as well as the intensity of the storm and the storm size. And for the storm size, it does this by setting the radius of maximum winds, or RMW, and it has a 3-member ensemble. And this is what I'm primarily going to be talking about in this talk. So for version 2.8, that was recently upgraded in the fall of 2020, the largest change was how we initialized the radius of maximum winds. So in version 2.7 and in prior versions, the RMW was set based on the slosh parametric wind profile, and often, it didn't match with what the best track RMW would suggest. So in this case, for Hurricane Barry from 2019, you can see that the small, medium, and large size storm RMW forecasts were far too small compared to the actual RMW. But in version 2.8 of P-Surge, when we initialize using the best track RMW value, we do a much better job of encapsulating the true RMW. But for the actual forecast of RMW, that methodology didn't change between version 2.7 and 2.8. So for P-Surge 2.9, we wanted to come up with a better way to forecast RMW. And there's a few different ways you could do this. You could use the actual RMW forecasts from global and regional models, such as the GFS and HWRF, shown here. These forecasts of RMW are from Hurricane Zeta from last year. And you can see that they're really quite noisy. There's a lot of run-to-run fluctuations, and this makes it challenging to use in operations. Even when you combine these forecasts into a corrected consensus, they're still really noisy and they're not very consistent. So instead, we decided to use NHC official forecast parameters as input into regression equations to forecast for RMW. So we use the initial RMW and then forecasts of intensity, latitude, and then the 34, 50, and 64 knot wind radii. And you can see that the resulting forecasts shown in the top right figure here are a lot smoother and a lot more consistent from run to run. This is much more useful for operations. The data we used to derive these regression equations came from 20 years worth of best track files going back to 2001. And because RMW doesn't receive the same level of quality control as some of the other parameters in the best track, we only looked at best track times that were within 120 minutes of aircraft reconnaissance, just with the idea being that those data would be a little more trustworthy compared to other times when we didn't have recon available. The resulting relationship between RMW and intensity is shown in the top right panel. And you can see that for the stronger storms, the RMW is a lot less, a lot smaller, and there's a lot of variance in RMW for the weaker systems. The two figures on the bottom illustrate that sometimes you have a very clear relationship between intensity and RMW, as was the case for Hurricane Matthew in 2016. But then for other cases, there's obviously other factors that are affecting RMW, like for Hurricane Jose in 2017. So we looked at 5 years of RMW forecasts from P-Surge 2.7, 2.8, and then 2.9 using these new regression forecasts, and just to see how the error and bias compared. And you can see that there was a large improvement through about 48 or 60 hours into the forecast, going from P-Surge version 2.7 to 2.8. And obviously, again, this is when we started using the best track RMW value to initialize the forecast. But by about 60 hours or so, there wasn't any improvement. Version 2.9, on the other hand, improves the forecast throughout the entire forecast period. We're also removing or reducing the negative bias in RMW, going from version 2.8 to 2.7. So these are example forecasts for Hurricane Laura. This is from version 2.7 of P-Surge. So this is what we had available operationally last year. And you can see that the RMWs were just way too small. By about 48 hours into the forecast, it happened to get the right answer for the wrong reason. We also are running version 2.8 in parallel last season. You can see that it started off with the correct RMW value, but the small, medium, and large size storms stayed too large throughout the entire forecast period. Laura was intensifying at this time, and the RMWs were decreasing. So it was evolving quickly. And using that information, we're able to forecast RMW, with more accuracy. And this is shown in the version 2.9 forecast of RMW. We just do a much better job of encapsulating the true value here. So how do these RMW regression forecasts affect the P-Surge forecasts? Well, we ran a series of retrospective forecasts for 13 storms between 2008 and 2018. And this spans the time of when we had USGS pressure sensor data available. We chose to focus on the greater than 3, 6, and 9 feet probability fields for forecasts that were initialized between 12 and 72 hours prior to landfall. And so these are the storms shown here in the figure that are in the retrospective set. So these are some results for probabilities greater than 6 feet. And they're shown at 60 hours prior to landfall on the left, and then 72 hours prior to landfall on the right. And these are rock figures that have the false alarm rate on the x-axis and the probability of detection on the y-axis. And so you can see that we're generally improving the probability of detection and going from version 2.7 to 2.8, and then again to 2.9. There is a slight increase in the false alarm rate, especially in version 2.9, but we think we can help bring that down by future improvements to P-Surge. Looking at the figure on the right, for forecasts that were initialized 72 hours prior to landfall, we can see that the probability of detection is relatively low. And I think this just speaks to the fact that we have a lot of work to do to try to increase the skill of the forecasts out at 72 hours lead time and beyond. These figures are reliability diagrams for probabilities greater than 9 feet at 48, 60, and 72 hours prior to landfall. At 48 hours prior to landfall, figure on the left, you can see that the reliability is definitely improved in version 2.9 compared to version 2.7 and 2.8. At 60 hours prior to landfall, there's perhaps a slight improvement in the reliability for the smaller forecast probability bins, but perhaps most importantly, we're starting to see some higher forecast probabilities of these high impact events out at 60 hours prior to landfall. This is something we haven't seen in version 2.7 and 2.8. So I think that's encouraging. Again, it speaks to the fact that these forecasts are starting to become more useful at longer lead times. And then 72 hours prior to landfall, I think, we still have, a lot of work to do to try to make those forecasts more useful. So one of the other benefits of version 2.9 is the greater run-to-run consistency, especially in the 10% exceedance values. So these are 10% exceedance values for Hurricane Harvey at 48, 36, and 24 hours prior to landfall for version 2.8, which is shown on the top, and version 2.9 on the bottom. And you can see that between 48 hours prior to landfall and 36 hours prior to landfall, there's a big change in the 10% exceedance values. And when the guidance changes drastically like this, it makes it very difficult to communicate the risks associated with a particular scenario. So having greater run-to-run consistency is a huge benefit and something we look for in operations. So just to summarize, the RMW regression forecasts that are based on NHC forecast parameters tend to be more skillful than the previous methods used by P-Surge to forecast RMW. And using these RMW forecasts in version 2.9 of P-Surge leads to improvements in reliability and increases the probability of detection for high-impact events. P-Surge 2.9 should become operational in about a month or so. The verification statistics of P-Surge version 2.9 at 60 hours prior to landfall are very similar to that of version 2.8 and 2.7 at 48 hours prior to landfall. And so again, I think we're just, it's another indication that we're helping to improve the skill of the P-Surge forecasts at longer lead times. And P-Surge version 2.9 tends to be more consistent from run to run. And this is an important aspect to consider for operational forecasting.